Well, I'm still in the mode of showing you kind of what the potential of the Fourier transform is for solving problems before I start dwelling on subtle questions about why it all works. So that's what you'll notice today. I'm being kind of loose with assuming limits exist and what I can do with them. Later on, I'll get much more careful about that. But today, I'll definitely be loose. Stein likes this example. He has it in a couple of his books in this series of solving the Dirichlet problem on the upper half plane. So we solved the Dirichlet problem on the unit disk, earlier in the semester, using Fourier series. Well, to solve the Dirichlet problem on the upper half plane, the Fourier transform is more amenable to that. If this was a class on complex analysis, I could show you via conformal mapping that you can always turn one of these problems, either the disk or the upper half plane, into the other by using a conformal mapping that is an analytic function that takes the upper half plane to the unit disk with an inverse that does the same thing. But we don't have that here, so I'm going to use Stein's argument here using Fourier transform. So the basic problem is I have the upper half plane there. That's the stuff above the x-axis. I'll call it the UHP. And I'm given a continuous function f of x on the real line. Think of that as the boundary temperature. And I'm going to assume that there's a finite there's a finite amount of energy involved, or at least not something that goes off and gets super hot. So I'm going to assume that the temperature along the real line goes to zero at either plus infinity or minus infinity. So there's not too much heat energy involved, especially when you're going way out. The problem is to find a harmonic function on the upper half plane that's continuous up to the real line and has that f of x as its values on the boundary along the real line. Okay, and so the solution to this problem, or at least how I'm going to find a formula for the solution. And in the end, I'm going to show you the formula is valid. But getting it, you're going to maybe think I'm getting kind of wild and crazy with limits. So the solution is, let's see, first of all, it's a heat problem. So this is a heat problem. It's actually a steady state heat problem. We assume that we slap on heaters and refrigerators to make the temperature on the real line f of x, and then we wait for the temperature to stabilize in the upper half plane. So it's a steady state heat problem. And the two-dimensional heat equation I'll take the, often there's a c squared here that is a constant depending on the thermal properties of the medium. I like to think of the upper half plane as a metal plate. Metal plates conduct heat pretty well, and the heat equation is the Laplacian is c squared times the Laplacian is du dt. But at steady state, this would be 0. Because it would stop changing. And so the problem is the Laplace equation. So the key is finding a function u that satisfies the Laplace equation in the upper half plane. And we want it to have that boundary value. So this is a problem earlier in the semester you had a homework problem about. We're going to try a u of xy of a special form, namely x of x times y of y. And you did this problem. And you found lots and lots of solutions, way more than in the Fourier series case, because there's no boundary conditions at all. And so when you try that and stick it in, so the Laplace equation is d2u dx squared plus d2u dy squared. Of course, we want that to be 0. And when I plug in these functions of the special form, the x derivatives would pile on the x function, so I get x double prime, and y would float along like a constant. And when they go on the y derivatives would pile on the y function, and x would float along like a constant. And you stare at that for a second and realize I can put all the x's on one side and all the y's on the other side and get x double prime over x equals minus y double prime over y. And of course, seen this enough times to know that the only way you can make a function of x equal to a function of y is if they're both constant. And so they're both we'd need them both to be a constant lambda. And so we've got two problems that are kind of familiar. Same old Fourier series problems. The x problem is x double prime minus x of x equals 0. And the y problem is y double prime plus, so they're different in this time, plus lambda times y equals 0. Of course, there are going to be cases now to think about. Let's do the case. If you think about what's the difference between x and y. X goes from minus infinity to plus infinity, and y goes from 0 to infinity. That's going to make these two problems different. And we're going to think differently about them. So let's do the case, how about lambda positive? Then I'll write lambda equals k squared. And that's going to be, k is going to be positive, and that's positive. So I'm taking k here to be a positive constant. Well, then the characteristic equation for that problem is r squared minus k squared equals 0. And we get r equals plus or minus k. And the general solution then is x of x equals c1 e to the kx plus c2 e to the minus kx. And those are, we're going to rule those out because if you think about it, this one goes to infinity as x goes to the right. That's not good. We don't want things to get hotter than hell. Okay. And this one goes to infinity on the other side. So this would go to infinity as x goes to the other side. Excuse me. So we don't want solutions that get too hot. especially at infinity, because we're expecting our data, f of x, is going to 0 for big X. So there's no way we were looking for solutions that are going to be immense out there. So we don't want solutions that get hot. Okay, so we're going to rule out that one altogether. No positive k's. And now let's think about the case lambda equals 0. That's pretty easy. Then the ODE is just x double prime equals 0. And the solution, you just integrate twice and you get x of x is ax plus b. And this one is the too hot one. But a constant solution wouldn't be so bad. Too hot as x goes to infinity. But the constant solution is okay. So we get x of x, take it to be 1. We're going to add up constants later. We're going to add these things up with constants in front of them. And so I won't write the b, I'll call it 1. And when I use it, I'll multiply it by something. Okay. Now I've got to think about the case negative. So that's going to be lambda equals minus k squared. That's less than 0. And just like before, I'm going to take my k to be a positive constant. Then we've seen this any number of times. The characteristic polynomial is that. And then we get r equals plus or minus ki. And when we didn't like complex numbers earlier in the semester so much, we get x of x equals, I guess I'll use c's, c1 cosine kx. We got real solutions from the complex ones. But now that we're getting more comfortable with the complex version, let's be more daring. Let's take the complex version. X of x equals c1 e to the I kx plus c2 e to the minus I kx. Those are bounded and wiggling. And that's going to be okay. At least they don't get too hot. They don't blow up. They keep wiggling far out, but that's going to be okay. In fact, we're going to need them to make the Fourier transform work. Okay, so now I've got some solutions, in the x at least, and now let's get the y functions. So next, get the y functions. Let's see. I got solutions in the case lambda equals positive k squared. That case, I got the x functions, or did I? No, those I ruled out that case, right? I'm sorry. Case lambda equals 0, I get the same y functions. Oh, let's see. What do I get? Sorry. The y problem. Okay. Okay, so I meant to say something here. Let me move this down. So let's see. I'm going to get solutions. I like to write it like this. X of x equals e to the I sx. Where s is either positive or negative. Okay. Okay, so now I'm doing the y problem. The case where I got, let's see, the case lambda equals 0, then I get the same old thing. We get the y of y is also a constant function. And then the next case that's interesting is lambda equal minus k squared. Then my y problem is y double prime minus minus k squared y equals 0. It's a different, the sign is different in the lambda spot in the y problem. And that's the exponential function. So r squared minus k squared equals 0 gives me r equals plus or minus k. And I get solutions y of y equals, I'm going to write them like this. E to the minus ky and e to the plus ky. We don't like this one because it blows up, it gets hot. We don't expect the heat to go blowing off to infinity in the y direction. So this one's too hot. So we're not going to use it. And now I'm telling you, here's all the solutions we found. We found a bunch of solutions that seem usable. Found u of xy equals x of x times y of y. And the x of x was an e to the I sx. And the y of y was e to the minus something. Let's see, s was the k. Let's see. We only took the positive k in the y variable. So the s is plus or minus k. I'm thinking here. S is equal to plus and minus k above. And notice that when s is equal to 0, we get the constant function. So this works for all s's. All the k, and the s's I'm writing for k. The s could be plus or minus k. That makes me think. So you think now what I'm gonna do? Like we did in Fourier series, you get a bunch of solutions. Well, then you start taking linear combinations. So the problem is linear. So I can do the superposition principle. The problem is linear. The Laplace equation is linear. So I can take linear combinations of lots of these functions. So let's see, the summation, who knows how many points I'll need, of Cn e to the I Sn x e to the minus absolute Sn y is a solution. Hopefully, if it converges nicely, it's a solution too. And you look at that for a second and think, SNs can be any old thing, not just n pi's or the Fourier series. They can be any old real numbers. And the SNs are plus and minus k's and in 0. So in fact, they go all over the place. And so the breakthrough moment is, this reminds me of a Riemann sum. And that means for an integral. And in fact, because the S is going all over the place, plus and minus, including 0, a Riemann sum for an integral from minus infinity to plus infinity something ds. And so now, my big idea is to try u of xy equals an integral. Let's see. When I write this down, I'm going to get some more inspiration in a second. I'm going to integrate this against the functions I found. E to the I s x e to the minus absolute s y ds. And you look at that for about 2 seconds and think, that's feeling kind of like the Fourier transform. So I'm going to put a 1 over square root of 2 pi in front. That's the big idea. And so you can, let's see, you can check, you can take the Laplace operator underneath that integral sign, hopefully. And, those things solve the Laplace equation. The e to the isx times e to the minus absolute sy, they solve the Laplace equation. We made them do that. And so that's going to show that the function u there is harmonic. And the question is, what happens as y, as y goes to 0, that's going to be, okay, so we don't know this, but if we assume the integral converges nicely, we can take the Laplace operator under the integral. To see that u is harmonic in the upper half plane. Okay, so we're going to assume that. And the last thing we want the value of this thing as y goes to 0 to be given. The last thing we want u of x of 0 to be equal to f of x. And if I stick in y equals 0 in that thing right there, that's 1 over the square root of 2 pi integral from minus infinity to infinity of g of s e to the isx e to the minus sy would be 0 ds, and we want that to be f of x. And the aha moment, again, is that we've seen that formula. That's the inverse Fourier transform. So this is we need this. This is the inverse Fourier transform of g is equal to f. Well, remember the Fourier, yeah, so that's the inverse transform. And so, in fact, what should f be? Oh, obviously, I'm sorry, g, I know what f is. F is given. Well, what should g be? If I want the inverse Fourier transform of g to be f, of course I need g to be f hat. And so now I think I might have a solution to the problem. Namely, u of xy equals 1 over the square root of 2 pi, integral from minus infinity to infinity, Fourier transform of f times e to the isx ds. And this is going to allow me to get the Poisson kernel for the upper half plane, because I'm just going to write it out as an integral and look at it. At least that's what Stein did. And so we're going to get the Poisson kernel. For the upper half plane. And here's how. I've got this formula right here. And so now I'm going to write it u of xy equals 1 over the square root of 2 pi. Let's see, my s is going from minus infinity to infinity. And my f hat is also an integral. So let's see. The f hat is 1 over the square root of 2 pi of integral from minus infinity to infinity of f of t times e to the minus s of t dt times, now I'll write e to the, oh, doggone it, I'm sorry, I skipped, back here, I skipped the e to the minus s y ds. I had to put that back in, sorry. Okay, that's fixed, but now I have this here. Okay, and now I use Fubini's. That's an integral in ds and dt from minus infinity to infinity. And so by Fubini's theorem, I can change the order of integration, hopefully. So Fubini's theorem, let's see, I would get 1 over 2 pi would come out in front. And then I'd change the order. So I'm going to have minus infinity to infinity. Now I'm going to do the dt on the outside and the ds on the inside. And when I do that, the f of t can be pulled out front of the integral. And then the integral in the ds part would go integral from minus infinity to infinity of, what do I get left? I'd get e to the minus st times e to the oops. What am I doing here? This is e to the minus ist. So I get e to the I s. This one is a plus x. This one is a minus t. Okay. And this one is an e to the minus absolute sy. and I'm integrating this ds. That turns out to be something you're going to compute explicitly. And it's going to be the Poisson kernel, basically. This is, let's see, the s is just a variable of integration, so this is going to depend on x minus t and y. And that's going to be the basic Poisson kernel. Let's see, I can just compute it. With my bare hands. So let's compute P. Let's see. I'm going to write P of x minus t comma y is going to be an integral from minus infinity to 0 plus an integral from 0 to infinity. Okay, the integral from 0 to infinity I'll do carefully. So it's going to be equal to integral from minus infinity to 0 plus integral from 0 to infinity. That's the one I'm going to write out carefully. Let's see. So that's s positive. So this integral is the s positive. We're integrating ds. So s is positive in that thing, and so that means what the function I'm integrating is, let's go back and look up here. This is the function I'm integrating. And when s is positive, the absolute value of s is just s. And so I get e to the is times something. So let's see, what is it? It's this one is going to be, I've got e to the s times I times x minus y. What did I have? Minus minus s. No, minus y. That's the function as s is going to go from 0 to infinity. And when you anti-differentiate that, what comes out in front is 1 over I times x minus y minus y. Okay. We've done calculations like this before with the complex exponential. And in that integral, s is the variable, so that stupid I times x minus y is just a constant, complex number constant. And so it looks intimidating, but let's see what happens when I stick in s equals 0. Oh yeah. Yeah, e to the s is 0, that would be just a 1 when s is 0. And when s goes to infinity, then the important thing here is that this s is going to infinity, and I've got minus y. And so that's a huge negative number. The modulus of that thing goes to 0. Okay, so I claim that this is going to be 0 minus 1 over I times x minus y minus y. And that 0 is because e to the minus sy goes to 0 as s goes to infinity in the integral. Okay, and you do the same thing for the negative one over here. in the negative one, then s would be negative. And the e to the minus absolute sy would be equal to e to the sy. So it's slightly different. But the calculation would be basically the same, and so I won't repeat it. And this time you would get a plus 1 over e to the I x minus y, x minus t. Difference here is plus y. And now you add them up. And they're easy. You just do the algebra and you add them up, and you get that p of x minus t y is something simple. 2y over x minus t squared, kind of mind-blowingly simple, plus y squared. That's the Poisson kernel for the upper half plane. Without the pi in front. So that's the Poisson kernel for the upper half plane. Now that we found it using Fourier transform, forget how you found it. And now we're going to show that it works. I'm not going to go through all the gory details. They're not gory. I should say I'm not going to go through all the beautiful details. My solution to the Dirichlet problem, let's say I've got a 2y there and I had a 1 over 2 pi. So in fact it's 1 over pi, integral from minus infinity to infinity, my given data function, that's the boundary temperature, times y over x minus t squared plus y squared dt. A formula for the answer that I guessed using Fourier transform and being kind of loose, in fact being extremely loose with the details. But I get this thing. That thing is harmonic in the x and the y. P of x minus ty is harmonic in xy on the upper half plane. So, and in fact, it goes to 0 at infinity fast enough that you can differentiate under the integral sign via differentiating under the integral sign. Via under the integral, which is justified because it goes to 0 at infinity so fast, which can be shown is allowed, which can be done because the kernel goes to 0 at infinity so fast. As t goes to infinity. So fast. Okay, and now we need to show that the boundary values are the right thing. And that comes from exactly the argument we did before. It's a good kernel. Okay, and that's the key to showing that if I wanted to prove that I have the right answer here, here's what I would do. Let's see, here's a graph. Let's see, here's my x. when y is kind of big, it's a bump. And it turns out the area under that Poisson kernel is 1, always 1. Because it solves the problem when the f is just the function 1. Anyway, let's see, if y is kind of big, we get a bump like that. So this is y pretty big. And the area under that blue curve is 1. But if I had a y that's getting close to 0, then my function would be small, pretty small, and the bump would be gigantic, about x like that. So the area under this would be 1, but the area would be concentrated very strongly near okay, so this green one is the y is small. And the smaller it gets, the more concentrated the area gets, just like all the good kernel things you've been doing in this course. And the area under the blue curve is red is 1 also. But for small y, it gets greatly concentrated at the x. So this is a graph of p of x minus t comma y. And the good kernel argument shows that the standard good kernel argument, that I won't do this time, I've done it enough times, shows that the u of xy, x naught, let's see, u of xy tends to f of x naught as the xy tends to x naught 0 from the upper half plane. So let's see, here's the x-axis, and here's an x naught. The xy is some point in here, getting close. This would be a radius delta. And I could use the good kernel arguments to show that I get the convergence to the thing I want. So that's how you can solve, or that's how you can be inspired to find the solution to the Dirichlet problem in the upper half plane. And it's an explicit, nice thing. Questions about it? Anything? Yeah.
Previous page with you're calculating the integrals on the right.
Yep.
Shouldn't that be 1 divided by I x minus t minus t? Yeah, on the right side.
Oh. Yeah. What the heck?
But also,
These things are t's here.
also
Thanks for catching that.
limit of
How does the limit go to 0?
You also missed one, the 0 minus 1 over I times x minus t.
Where?
On the bottom right, the 0 minus 1 over I times x.
Yeah. This one. At least I have it good correct on the left-hand side. Sorry. What?
so you have the limit of like
Right, so e to the I, that's a good question. I was kind of in a hurry back there, but let me do it down here. Let me copy this thing here. Let's see, so what is this thing? This is equal to e to the I times s times x minus t minus s times y. Okay, and that is e to the I times s times x minus t times e to the minus s times y. And so if I take the modulus, that would be the modulus of this one times the modulus of this one. This is on the unit circle. E to the I theta is on the unit circle. E to the I theta is on the unit circle, so this modulus is 1, and this is a positive real number, so this modulus is e to the minus sy. And so as s goes to, in the upper half plane, as s goes to plus infinity, y is greater than 0 because we're in the upper half plane. And so as s goes to infinity, this goes to 0. That answer your question? Yeah, that's why. Kind of technical, but nothing earth-shattering there. As long as I can get away with all the Fubini theorems and assuming I can differentiate it under integrals, etc., then I get a formula in the end which I can then show is valid. And you'll find this a lot in math and science, especially in the engineering field. You do whatever you want to find a solution, and then when you find it, you show it that it works, and you forget how you found it. You'll see it again and again if you take engineering classes. And that's kind of historically how these things were discovered. They cheated to discover them. And if you get used to that, you'll discover things too. Physicists do it all the time. In fact, the Feynman integral was just, for a long time, nobody believed it was even true until they figured out a way to make it rigorous. So yeah, sort of math catches up with history and a lot of our work is to show that these things can be made rigorous and precise. Okay, that feels like enough for today. The next homework I've posted now, it's not nearly as long as the last one, so it should be more fun.
So you were talking about the conformal mapping.
Yeah.
So if we just Cayley transform this
Right.
into the unit circle, we could.
Then you can
just
pull
use
back.
the-
Then you have to think about what you mean. Yeah, so let's see. The going to 0 and infinity would just mean that when you do the change, you get bounded. Right.
Yeah.
So you get bounded things with one possible weirdness at the where the point of infinity